Sorting data. It seems so simple, right? Just put things in order. But believe it or not, it's one of the most fundamental challenges in programming. Getting it right is an absolutely critical skill for any developer, mainly because the best way to sort is almost never obvious. So how do you pick the right tool for the job? Let's dive in.
I mean, really think about it. It's a simple problem on the surface. But if that's true, why on earth do programmers have this whole arsenal of different algorithms to choose from? It's a fantastic question, and the answer, well, the answer gets to the very heart of what it really means to write smart, efficient code. And there you have it. There is no single best sorting algorithm. It just doesn't exist. Every single one comes with its own unique set of strengths, weaknesses, and trade-offs. The real skill isn't knowing one algorithm, it's knowing which one to pull out of your toolbox for which specific job. So before we meet our contenders, let's just quickly nail down why this matters so much. Sorting isn't some academic exercise you do in a classroom. It is everywhere. I mean, literally everywhere. Every single time you see ranked search results on Google, or a neatly organized spreadsheet for a report, or even when you're just trying to make sense of massive, messy log files, sorting is the unsung hero doing all the heavy lifting behind the scenes. It is the very first step in turning total chaos into useful, organized information. All right, let's meet our first two contenders. These are the kinds of straightforward, intuitive approaches you might even come up with yourself if someone just handed you a shuffled deck of cards and said, put these in order. First up, we've got selection sort. Let's call it the methodical scanner. So imagine you have a pile of cards spread out on a table. Selection sort just scans the entire pile, finds the absolute smallest card, the two of clubs maybe, and puts it in the very first spot. Then it scans the rest of the pile, finds the next smallest, and puts it in the second spot. It's simple, it's predictable, it's methodical. And you can see that process right here. On the first pass, it scans everything, finds 65, and swaps it into the first position. On the next pass, it finds the next smallest, 72, and puts it in place. It just keeps doing this, step by step. Now, the key thing to notice here is its predictability. It's consistent, sure, but its one true advantage is that it makes very few swaps. And that can be a huge deal when writing data to memory is an expensive operation. Okay, next up, meet insertion sort, our adaptive organizer. Now, this is probably how you actually sort a hand of playing cards. You hold the cards you've already sorted in one hand, you pick a new card from the pile, and you just kind of slide it into the correct position among the ones you're already holding. Let's watch it go. It starts with a perfectly sorted list of one item, 88. Then it picks up 72. Sees it smaller, shifts 88 over, and pops 72 in front. Then it takes 93, no shifting needed there. But then it gets to 65 and has to shift everything down to make room at the very beginning. You see, it's constantly growing a sorted section of the list. Okay, now this is where insertion sort gets really, really cool. It's adaptive. What does that mean? It means its speed totally depends on how sorted the list already is. If you give it a list that's already pretty much in order, it just zips right through. We call that linear time, or O of n, which is incredibly fast. But if you give it a list in perfect reverse order, the absolute worst case scenario, it grinds to a halt, because it has to shift every single element for each new item it adds. So we've just seen two simple strategies that, they work pretty well for smaller lists. But what happens when you're not dealing with a deck of cards? What if you have a massive data set, millions of items? For that, we need a completely different strategy. We need to divide and conquer. And this brings us to the heavyweight champion, merge sort. Let's call this one the master planner. Instead of trying to wrestle with the whole list at once, merge sort's genius is to break the problem down into smaller and smaller pieces. It splits the list in half, then splits those halves in half again, and it keeps going until it's left with a bunch of tiny lists with just one item each, which are, by definition, already sorted. And then the magic happens. It starts merging those tiny sorted lists back together. It takes the 88 and the 72 and merges them into a new sorted list, 72, 88. It does this all the way back up the chain, masterfully combining sorted pairs into larger and larger sorted lists, until, boom, the entire array is perfectly in order. But, and this is a big but, here is the crucial trade-off.
Merge sort's performance is the gold standard. We're talking a guaranteed, predictable O of n log n speed, no matter what the data looks like. It's incredibly reliable. But that power comes at a price. To do that clever merging step, it needs extra memory. It has to create a temporary array to build the sorted list in. So, yeah, it's blazing fast, but it's not free.
All right, we've met our 3 contenders: the methodical scanner, the adaptive organizer, and the master planner. Now, it's time for the main event. We're going to put them head to head and figure out how to choose the right champion for the job. So, the crucial trade-offs, they're all right here on this table. We've got time complexity, that's basically speed. We've got space complexity, that's memory. And we have this really important concept called stability. A stable sort just means that if 2 items are equal, their original order is kept after sorting. As you can see, selection and insertion sort are slower on average, but they use no extra memory. Merge sort is way faster, but at the cost of using up more space.
Okay, time for a little pop quiz. You've got a small list of data, let's say a few hundred items. It's already mostly in order, and you don't have a lot of extra memory to play with. What's your pick? Which algorithm do you choose?
It's gotta be insertion sort, right? This is its absolute perfect scenario. Because the list is nearly sorted, it gets to use that adaptive superpower and just fly through it. And since memory is tight, the fact that it uses basically 0 extra space, what we call sorting in place, makes it the clear champion here. Okay, scenario number 2. Now you're dealing with millions of records. The data is completely random, a total mess. And this is critical. You absolutely must preserve the original order of any items that have the same value. What's your choice now?
Yeah, this is a job for merge sort, no question. For a massive dataset, you just can't risk the slow O of n squared performance of the simpler sorts. You need that guaranteed O of n log n speed. And because preserving the order of those equal items is crucial, you need a stable algorithm. Merge sort checks both of those boxes perfectly. It's the reliable heavyweight.
So after all that, what's the one big idea? What's the main lesson we should walk away with from all this?
It's this. Choosing an algorithm is not about memorizing which one is the fastest. It's about being a detective. You have to investigate the problem itself. How big is my data? What does it look like? Is it random? Is it almost sorted? How much memory can I afford to use? Is stability important? The best choice is always an informed one.
And that leaves us with one last thought to chew on. We saw that for certain problems, the simple insertion sort actually beats the more complex merge sort. It really makes you wonder, doesn't it? What other complex-looking problems, maybe in our work or even in our lives, might have surprisingly simple, elegant solutions if we just took the time to truly understand the specific conditions of the job? Thanks for joining me.